Good morning, in case it's morning. Okay, so today we will finish up our discussion of the CCFT, at least the normal CCFT. Later on, we'll talk about the distribution version of the Fourier transforms. But today we'll finish off the sort of regular version of the CCFT by talking about the L2 CCFT. Okay, so the CCFT, like all of the Fourier transforms, has a natural domain of definition, just by the way it's defined, of being L1. We saw that for the CDFT, we saw that for the CCFT. We will also see that a little bit later on today for the DCFT. And for the DDFT, that's kind of a trivial assertion because the DDFT is has a finite dimensional domain and codomain. Okay, so L1 is the natural domain. And for the CDFT, because L2 per is contained in L1 per, the L2 CDFT is obtained merely by restriction. However, for the CCFT, life is more complicated. And the reason is that L2 is not a subset of L1. Okay. And so I have the convention where omission of the possible equality means strict inclusion. Okay. Okay, so if you're going to define the L2, the CCFT for something in L2. So if F is in L2, then this integral does not exist in the normal sense of the Lebesgue integral. Okay, so if you're going to define the L2 CCFT, it's not going to be by writing down that formula. Okay, doesn't stop people from doing it all the time, but nonetheless. Okay, so the approach to defining the L2 CCFT is indirect, I guess I would say. And here's how the construction goes. So the construction is sort of straightforward. It involves a list of verifications that I'll tell you what the verifications are, but not verify them. All of the verifications are more or less just direct. You just look at the thing you're supposed to prove and do the calculation. Okay, so it's one of those kind of the proofs of the assertions that I'm going to make here are of the uninteresting variety. Okay, good. So we're going to start with an F in L2. Okay, now, so the construction involves building certain sequences. Okay, so I'm going to define Fj to be, and all I'm going to do is I'm going to take the function f, and I'm going to truncate it from -j to j. Okay. All right, so the idea is that we have our function f like this. Let's say -1, 1, -2, 2. Okay, and so f1 is going to be okay. Then f2 is going to be like so, and so on. Okay, so in an increasing sequence like that. Okay. right, so an easy fact, and so this one I'll explain why this is so, is that Fj is in L1 intersect L2. Okay, so why is that true? Okay, so first, F is in L2, and so it follows, therefore, that each of these is in L2 on its support. Okay, so if I take the compact interval minus jj and truncate f, so the support is in the compact interval minus j to j, then the resulting truncated function is going to be in L2 of minus j. Okay, and that's just because obviously the integral from minus j to j is less than or equal to the integral from minus infinity to infinity. Okay. So that's true. Now L2 of the compact interval minus jj is in L1 of that same interval. Okay. Because on bounded time domains, remember that big L1 is a subset of big L2. That's one of the things that we proved that a long time ago. And so since it's in L1 on this compact interval, it's also in L1 on the entire real line because it's 0 outside the compact interval minus jj. Okay, so that's why that's true. Okay. Now, the first of our facts that we're not going to prove, but as I say, it's just a direct verification. Just take the thing that you need to be true and you calculate it. Okay, and the first of these assertions is that the CCFT of L1 intersect, oh, sorry, we'll spell it out here, L1, L2 is in L2. Okay, so I know something being in L1 ensures that it's in C00, okay? But if I additionally require that F be in L2, then I conclude something different than it just being in C00. It's in C0, but it's also in L2, okay? All right, so that's one fact. And so therefore, another fact, and this one isn't necessary for the proof, but it's kind of makes sense of some of the constructions. This sequence Fj that I built by successive truncations converges to F in L2. Okay, so in the L2 form. All right, so what I'm really saying here is that L1 intersect L2 is dense in L2. That's exactly what this says. So if I take an F in L2, I can build a sequence in L1 intersect L2, namely this one, that converges to F in L2. Okay. Okay, so more germane to what we're doing here. So again, this fact, oops, these two facts are just directly verifiable, as is the following. Okay, and that is that the sequence of CCFTs, okay, which now makes sense because Fj is in L1, okay, so those have the usual definition just directly in terms of the integral. That sequence of CCFTs is a Cauchy sequence in L2. Okay, and this is not unrelated to the previous fact. Okay. Alrighty. And finally, define the CCFT of f, okay, to be the limit as j goes to infinity, fcc of fj, okay, and the limit, of course, is in L2. Right? And so here I'm using the fact that L2 is complete, right? Because I have a Cauchy sequence, and completeness ensures that the Cauchy sequence converges. So this definition makes sense, okay? All right, and so a caveat here, I'm going to use the same symbol for the L2 CCFT as for the L1 CCFT, all right? But the two things have different definitions. Okay, so if f is only in L2 but not in L1, then I'm going to use this limit definition. Okay. Okay, so all right. So if f is in L1 intersect L2, so both constructions apply. So then the L1 and L2, these constructions agree in the following sense. So they agree in L2. Okay, so they build you the same function in L2, meaning it's really an equivalence class of functions. Okay, so so the CCFTs of f agree in L2, and so what that means, therefore, because if f is in L1, I know that its CCFT is continuous. Okay, and what this means, therefore, is that for this particular f in L2, there is a natural representative of the equivalence class, and that is the continuous one that comes from the fact that f is also in L1. Okay, so there's some thinking you should do to unravel all of that stuff. Okay. All right, so the other thing to notice is that the L2 CCFT is not a pointwise construction. Okay, that is, it does not give FCC of f of nu for nu in R. Okay, so it doesn't tell you what the value of the Fourier transform of f is at a certain frequency. It just tells you what f is, or sorry, what the CCFT of f is in L2, okay, as an equivalence class. Okay, and so, you know, if you give two prescriptions of the value of this function for every frequency, what you do know is that they will agree almost everywhere. Okay. And this manifests itself in this kind of construction here. So, for example, you know, you might, so we've built in this definition of the L2 CCFT a very specific sequence Fj, which has some properties that I listed here. Okay. Now you can define other Fjs in L1 intersect L2 that approximate f. Okay, in this sense, okay, and it turns out, therefore, this thing is Cauchy. Okay, and therefore you can define the CCFT, and the limits will agree in L2, meaning almost everywhere. If you think of the equivalence classes of those functions, they agree almost everywhere. But it's possible you can make two different sequences, calculate kind of pointwise limits, and the pointwise limits may be different. Okay. Right, so really this is the L2 CCFT should be thought of as being a mapping from L2 to L2, and it maps equivalence classes to equivalence classes. Okay. All right, so okay, so we have this construction like this. And so just like the CDFT, it has this nice symmetry at the index 2, right? So so it maps L2 into L2. And we know that this now, as we've talked about, is a Hilbert space. Okay, it has a natural inner product. Okay, so moreover, okay, since L2 is a Hilbert space, with, just to remind you what the inner product is. Okay, so keeping that in mind, it is so say it so that it makes grammatical sense. The following assertion makes sense, and moreover is true. Okay. Okay, so the L2 CFT, like the L2 DFT, is a Hilbert space isomorphism. Okay. With this as inner product, okay? And that was true for the CDFT as well. And there we had, it was kind of, here in the continuous case, the spaces are the same. But for the CDFT, of course, they were different. One was continuous, the other was discrete. And so they had their specific inner products, okay? And as long as you define those inner products in the right way, then the appropriate Fourier transform is an isomorphism of Hilbert spaces. Okay, so remember that for the CDFT, so just to remind you, because if you don't make the right choices of inner product, then the statements that it's nice Hilbert space isomorphism are not true, but they're true up to an annoying constant. So it's much better to just make the definitions of the inner products correct, and then you have the isomorphism property. And so remember, for the CDFT, the discrete inner product that you use is, so there it was in the frequency domain, so I'll write the functions there as G. So And then remember that we had a coefficient out front, and so the rule when working with Fourier transforms is that you, whenever you have a sum over discrete times, like I do here, out in front of the sum, you should put the sampling interval, which in this case is delta. And as long as you do that slavishly all the time, then all the nice statements work out to be true about Hilbert space isomorphisms and so on. Okay. All right, good. So let's maybe some examples. Okay. So let's let f of t be 1 over 1 plus absolute value t. Okay. And so this is in L2. But not L1. Okay. All right, and that's just because its rate of decay at infinity, which is 1 over t, isn't fast enough to give you something in L1, more or less, because when you integrate 1 over t, you get logarithm, which blows up at infinity. But the rate of decay for the L2 norm, because you, of course, square f, becomes 1 over t squared, which is then integrable, so f is in L2. Okay. All right, so now this will be an example which of a signal that has no L1 CCFT, but has an L2 CCFT. Okay. So we can define the CCFT of f as a limit in L2, just like in the construction above, but the definition in terms of this integral does not make sense. Okay. So it turns out, despite the fact that the CCFT is not in L1, so it turns out that the CCFT is in fact continuous. So you can actually, plug this into a symbolic manipulation package like I use Mathematica, but there are others. And ask it to calculate the Fourier transform by just asking it to calculate that integral, or use the built-in Fourier transform function, and it will give you an answer. Okay, and it's giving you an answer in this limit sense, and it turns out that even though f is not in L1. Okay. We have okay, and so the CCFT has the properties of the L1 CCFT, namely that its transform is continuous and decays to 0 at infinity. And its transform, sort of And so where does the badness kind of, you still maybe expect there to be some manifestation of the fact that F is not in L1, and so there should be something kind of weird about the CCFT, you think. Okay, and it's the transform kind of looks like this. I forget the formula for the function, but it looks like so. And it doesn't blow up to infinity here. It has a finite value at 0. Okay, in the limit. Okay, so so what this means, so you have to be careful about what a statement like this means, because the CCFT of F does not have a pointwise value. But what this really means is that there is a representative of the CCFT in L2, which is in here. Okay, so you have to be a little careful with the kinds of statements that you make. Okay, so okay, so take the function, which is 1 on the interval -1 to 1 and 0 elsewhere. Okay, so we've actually looked at this one before. Okay. All right, so now there's no problem with this F. Of course, it's in L1. Okay, and we've calculated its CCFT previously. It's a Dirichlet kernel. Okay. Now, why am I talking about this? Well, note that the CCFT of F is not in L2. Okay. All right. And so, but somehow, and so therefore, therefore the Fourier integral corresponding to F does not exist in the normal sense. Okay. All right. And so if you're going to calculate the inverse Fourier transform, it's not going to be by that formula. Okay, but we've looked at this example before. Okay, as an example of pointwise and uniform convergence of Fourier integrals. And so what we decided then was that the family of Fourier integrals, okay, so maybe I'll write this down carefully. Okay, so these were the partial integrals, like partial sums, right? Okay, so these were the integrals from minus omega to omega, right? And then, you know, we had the integral from minus omega to omega was a convolution with the Dirichlet kernel, and so that's where this notation for these partial integrals came from. Okay, so if you forget that, you should look back on that stuff. Okay. All right, so we showed that this family converged pointwise to this function, which was 1 between -1 and 1, and 0 elsewise, and at the point of discontinuity had the value of the average of the left and right limits, right? So this was Dirichlet's test. Okay. Okay, so what's kind of going on here? So we know that. Oh, I'm sorry, I said something wrong here. I meant L1. It's not in L1, it is in L2. That's the whole point of this discussion, okay? And so because it's not in L1, this integral does not exist in the normal sense, okay? But previously we had the limits of the partial integrals converged pointwise, okay? And we also know that the CCFT of f, okay, given by that formula, is in L2. Why is it in L2? Well, it's in L2 basically because at infinity it behaves like 1 over nu squared. Okay, and so on any finite compact interval around 0, it's bounded. Okay, that function is bounded if you take its limiting value at 0. And at infinity, it goes like 1 over nu squared, or sorry, its square goes like 1 over nu squared, and so therefore it's in L2. Okay, all right, so let me record that. So, but f, not f, but the CCFT of f is in L2. Okay, and so the very same construction that I used up here, okay, this construction of the CCFT using these approximations, and you know, just because the formula for the CCFT is exactly the same as that for the Fourier integral, except for that sign there, this precise construction will also work with the Fourier integral, and so you'll get a sequence that converges in L2. So one can define f capital Fj, which is going to be, again, you truncate the function on the interval minus j to j. And note that if we write fcc minus 1 of fj to be the normal integral over the actual Fourier integral. I'm sorry. Fj of nu, 2 pi t nu, and now this definition, this construction makes sense because these fj's are in L1 intersect L2, so the integrals, there's no problem with those integrals, and so these will be the partial. These are going to now be exactly the partial Fourier integrals, because of course this is just the integral from minus j to j fcc of f nu e to the 2 pi t d nu. Okay. Okay, so if we define this thing, then these are in L2, just like they were for the forward CCFT, and they are a Cauchy sequence that will therefore converge in L2. Okay. Okay, and so I can therefore define the inverse L2 CCFT in exactly the same way as I defined the forward L2 CCFT, and then I get that I can make sense of the inverse CCFT of the CCFT of F, okay, by this limit, okay, and okay, F of T will be, and now the difference here is that this limit is happening in the for signals in the time domain, whereas for the forward CCFT this limit was being done in the frequency domain. Okay, and because the CCFT is an L2 isomorphism, whatever this limit in L2 is, okay, it will agree with F almost everywhere. Okay. All right, and so in this case, the interesting thing that goes on is not with the forward transform, but with the inverse transform, okay, using Fourier integrals. And so we see here that we had this construction already, these partial integrals that we had defined when we talked about convergence of Fourier integrals. These are, if you just replace omega with J, right, these are exactly these approximations here. Okay, so in other words, what I'm saying is that this is actually DJF of T. Okay. All right, so there's this nice connection between the L2 transform and the Fourier integral approximation results that we had previously. Okay. All right, so that is the L2 CCFT. Okay, so later on, we're going to talk about a continuous time Fourier transform. So that means CDFT and CCFT for distributions. Okay, and there's a very elegant story there, which is kind of hard to dig up. And so I want to sort of display that. But before we get there, we're going to finish talking about the normal, the non-distributional Fourier transforms. So there's two more of those to talk about, the DCFT and the DDFT. Okay, so these ones are significantly easier than the continuous time transforms for two reasons. One is that they're defined using sums, not integrals, and the other is they benefit already from a lot of work that we've done previously for the CDFT. A lot of the work for Fourier series, which, so Fourier series are the inverse of the CDFT, and so it should not be, aesthetically surprising that the inverse of the CDFT is very much related to the DCFT. Okay, so that's what we're going to see. Okay, so the DCFT. All right. Okay, good. So what should its definition be? Okay, so just again by analogy. And so we kind of, vaguely suggested our definition of the CCFT by analogy with the CDFT. Here we're going to define the DCFT by analogy with the CCFT. We're going to kind of, discretize the CCFT. Okay, so by analogy with the CCFT, okay, FCD. We talked about this before when we first introduced Fourier transforms. Okay, all right. So the F here is going to be a discrete time function, and the resulting transformed function will be a continuous frequency function. So it'll be a function of a continuous frequency, which is new. Okay, and you're going to replace the integral with a sum. Okay, then it's going to be f of, and so f is itself a discrete time function defined on a sampled discrete time domain with sampling interval delta. Then it's e to the minus 2 pi I. Okay, now here, remember for the CDFT, we had NT over T, okay, and so what was the role of T there? Well, 1 over T was the sampling interval, so in the frequency domain, here, the sampling interval in the time domain is delta, and so, and T gets replaced with nu, because it's continuous frequency. All right, so, whether you buy all those analogies or not isn't too material. The point is that the transform is defined like so. Okay, and then you apply the rule that whenever you write a summation over a discrete time or frequency for Fourier transforms out front of the sum, you just stick the sampling interval. Okay. Okay, all right, so so it's maybe a good time to recall the standard nomenclature, because it's not the nomenclature that I'm using. I'm using nomenclature which, in my opinion, is better than the standard nomenclature. That's often the case, that nomenclature turns out to be defective or has limitations that only appear later. Sometimes, unfortunately, tradition keeps the poorer notation in common usage, but the standard nomenclature is what I call the CCFT, is what's called the Fourier transform, just Fourier transform with no prefixes on it. And this thing, which I call the DCFT, is what's called the discrete time Fourier transform. So if you see the standard literature, that's probably the terminology that you'll use, or that you'll see. Hopefully you'll use the terminology that I'm using, because I think it's better. Okay, and I'm not going to take credit for this. Again, I mentioned this before, but this terminology of CCFT, CDFT, and so on comes from a very nice book on signals and systems by Quackernack and Saban. Okay, so the book has many other nice aesthetic attributes. Okay. Okay, so in any case, this is going to be the definition of the DCFT. All right. Now, what's the domain of the DCFT? Okay, so what property should F have in order for this to make sense? Well, the arguments are exactly the same as they were in our previous cases, and that is that we're going to require that the summands here form something in little L1, right? And because the summand is a product, one component of which has modulus 1, it really amounts to this being in little L1. Completely analogously to what we've had for the CDFT and the CCFT. Okay, now what about the codomain? Okay, so now if F is in little L1, okay, so we've seen this argument before, then what do I have here? I have a collection of functions of the continuous frequency variable nu, and the components and I'm summing them, and the summands are bounded by something which is in little L1. That's exactly the assumption that I've made here. And so by the Weierstrass M test, this sum converges uniformly to something in C0. And so you get something that's continuous, periodic, and the period is 1 over the sampling interval in the time domain. So just like in the time domain, we had periodic time t led to sampling interval and frequency of 1 over t. Here we have a sampling interval in time of delta, okay, and then a period in the frequency domain of 1 over delta, okay. So you don't have to memorize a lot of stuff here. You just, if you understand some of the basic principles about how things Fourier want to work, they do work that way. Okay. Okay, and so this is true by the Weierstrass M test. Okay, good. All right, examples. Okay, and I'm not going to, so again, the point here is not to be computational. You know, just purely computational aspects of Fourier theory is incredibly dull. And so I want to keep things on kind of a conceptual level to, so the examples don't illustrate how to do computations. In fact, I'm not going to do the computations. The examples are meant to illustrate interesting things. All right, so the along those lines, the examples I'm going to look at should echo things that we've talked about before. Okay, so I have just discrete time signals here, like so. All right, and so I'm going to go here. I'm going to define a signal which goes out to minus n delta in this direction and delta in this direction. I have no idea if the number of intervals agrees. It looks like this one certainly has more, but that's fine. Okay, and so these things are going to have value 1 between minus n delta and n delta. Okay, so it's going to be like this. So this is an example of something that we looked at in the continuous time case, but now we've sampled it. Okay, so this is a sampled window from minus n delta to n delta. So I guess I forgot, or actually I think I'm just going to move this thing here. Okay. All right. Now, what happened in when we took the CCFT of the continuous time version of this thing, right? And so that went from, I think we decided on minus A to A. What we got out of that was one of the Dirichlet kernels, and it was D sub A, okay, the continuous time Dirichlet kernel, all right? Or sorry, the aperiodic. They're all continuous time. One's periodic and one's not. Okay, so what happens here is in the time domain, we're taking a signal, namely the continuous time signal, which is 1 from minus n delta to n delta, and then 0 outside, and we're just sampling it. Okay, and so what happens to the transformed signal is the sampling in the time domain. Sorry. Okay, so the sampling in the time domain leads to periodification in the frequency domain, right? And this is something we're going to talk about. Okay, but in any case, when you calculate the DCFT of this thing, what you get is you get the periodification of the CCFT of the continuous time version of this. Okay, so that's very, very elegant. Okay, so you get the periodification of the Dirichlet kernel, and we sort of talked about periodification of these Faget and Dirichlet kernels before. And you get a delta out there, and this delta that you get there is exactly that delta, right? And so you get D per, sorry, so the periodic Dirichlet kernel, then T is the period, which is 1 over delta, and then it's n, where n is that n, okay, of the continuous frequency variable nu. Right, so sampling in the time domain leads to periodification in the frequency domain. Okay, then let's look at another thing that we looked at in the continuous time case. All right, and again, we're going to have this n delta and delta, and then we're going to just do a triangular wave function like so. Okay, so it's, if you like signal processing, this is a triangular window in time. Okay, and so we, in the continuous time case, we decided that the CCFT of this thing was the appropriate Faget kernel. And again, in our window in the continuous time case had width from minus A to A, and we got some, the Faget kernel, which was indexed by A. Here we're going to get the periodification of that in the frequency domain. And so it's FCC of F of nu is, and then you get this delta, which again just comes from our particular definition of the transform for delta minus 1 and okay. All right, so now we've seen the same kind of thing happen in 3 different cases, and we're going to see that it happens in a 4th case as well, and that is there's these window functions. You have a rectangular window and a triangular window. Okay, and the transform gets connected to these kernel functions, okay? And so for the CDFT, okay, we had the windowed function. It gave rise to gives you the sampled the sampled version of the Dirichlet kernel. So you get a sampled. I'm not going to be able to write this down in an organized way in less than half an hour. So sorry, I'm just going to stick to the verbal descriptions. Okay, so for the CDFT, what did we do? We took a window function like this one, okay, except it was periodic now, okay? So it was periodic continuous time. And then when we took it CDFT, what did we get? What we got was we got a discrete frequency signal, which you got by sampling the continuous aperiodic Dirichlet kernel, okay? And then similarly here with Fourier kernel. Right now, for the CCFT, you took the continuous time version of this window function, and then you CCFT'd it, and you got the continuous time Dirichlet kernel not sampled. Okay. Now, in this case, you sample in the time domain, and then you get the periodic version in the frequency domain. Okay. So there's this, and these are just examples, of course, but the fact is these examples reflect something general. Okay, which we will talk about, but I just want to point them out for these examples because these examples are nice because our kernel functions show up that seem to be important. Okay. So the DCFT has elementary properties. Like those of the CDFT and the CCFT. Okay, and by that I mean, you know, it's linear. It behaves in predictable ways with respect to, you know, flipping about the a dependent variable axis and so on. Okay, shifting and stuff like that. Okay, so there's standard things there that I'm not going to repeat here. You can look up the precise statements. Okay. Now, if you think about our previous discussions of Fourier transforms, what was the next thing that we did? The next thing we did was we talked about regularity of the signal versus rate of decay of its transform. Well, that doesn't quite make sense so readily here because, excuse me, our time signals are discrete time, and so, you know, saying a discrete time signal has a lot of regularity doesn't make sense. Differentiability doesn't make sense there. Okay, so you have to think about doing things the other way around. So what you can have is you can have discrete time signals that decay quickly as discrete time signals, and that should lead to regularity for the transform signal. Okay. All right. So rate of decay and regularity. Okay, so for the CDFT, it kind of went the other way around, right? It went regularity and rate of decay because we had a continuous time and discrete frequency. And for the CCFT, we had both things, right? We had rate of decay in time versus regularity and frequency, and we had regularity, rate of decay, I forget what I just said. Anyway, you have rate of decay in one and regularity in the other, and then regularity in the other versus rate of decay in the one. Okay, So here we have rate of decay and regularity. And so you get a result that looks very reminiscent of our rate of decay conditions for the CCFT, giving rise to regularity for the transform. Okay, so here's what it is. Okay, so I have a discrete frequency signal, F. Okay, and I'm going to ask that that signal be in little L1. Okay, and so, so I'm multiplying F by this thing which blows up at infinity. And so this tells me that F has to decay at infinity fast enough so that even though I multiply it by this polynomial t to the k, it's still going to be in L1. Okay. So that's a rate of decay condition on F. And unlike in the continuous time case, where a condition like this doesn't necessarily make reference to any kind of rate of decay, because this can be in L1 without even decaying to 0 at infinity. But in the discrete time case, it really, really does mean it's really a rate of decay condition. Okay, so then FCC of F is in, sorry, DC is in CK per T. Okay, and you have a formula for the derivatives of the transform. Okay, and you get just what you expect by just looking at this formula and naively differentiating with respect to nu. You get factors of 2 pi I and delta that come out front. Okay. All right, so it's delta sum n z of -2 n delta to the k f of n delta e to the -2 pi delta nu. All right. Okay, and this you can just verify quite directly using standard results from your analysis about switching derivatives and sums. And so you ascertain that this condition allows you to swap the kth derivative with the sum. And so that gives you directly. Okay. So notice also that this result applies to Fourier series. Okay, so if you have a Fourier series whose coefficients decay in such a way that now as functions of frequency, you get a condition like this. And so, so I'm just going to scribble on the side here. So I mean that if the function f has the property that it's CCFT, sorry. Okay. Sorry. Okay. So if the function f, yes, sorry, I had it right. So nu goes to nu to the k f cc of f of nu. Sorry, I'm working with CD here. Apologies. Okay. All right, so now here, this is a discrete, just like this in this result, t is a discrete time. Here, nu is a discrete frequency, just because I'm working with the CDFT. All right, but if f has the property that this is true, then what's true then is that okay, then you can conclude that f is in CK per T. Okay, and you have to be careful here because it doesn't necessarily mean that f is in CK per, but it means that it's equivalent to, so it agrees almost everywhere with something that's in CK per. Okay, so you can kind of do this as a the backwards version of this to get converse conclusions for rate of decay in the frequency domain versus regularity in the time domain for the CDFT. Okay, so that's sort of an aside here, which is useful. Okay, good. All right, so still talking about the DCFT inversion. All right, so DCFT inversion is very simple. You can explicitly calculate the inverse. So if f is in L1, sorry, then we can recover f from the DCFT of f by the inverse FDC inverse. Okay, so it's a slight abuse to write FDC inverse because the CDFT is injective, or sorry, the DCFT is injective, but it's not surjective. But nonetheless, I'm going to write this as an inverse. And it's going to have this domain. Okay, and the price I pay for the fact that the DCFT is not injective is that this isn't in L1, but I do know that it's in little c0 just because of the fact that the CDFT of something that's continuous, and so therefore in L1, L1 per will have a CDFT in little c0, and so we're flopping the roles of frequency and time here in going from the CDFT to the DCFT. So this is really a statement that we already know for the CDFT, and we're just applying it to the inverse of the DCFT. All right. And we have a formula for this, and it's just the forward transform for the CDFT with the obvious modifications. Okay, so it takes a continuous delta 1 over delta periodic function of frequency, which is capital F, and returns something in little c0. Okay, and the formula is so it's going to be n delta is simply going to be the integral. So again, the formula for the forward DCFT with modifications. Okay, corresponding to the fact that it's the inverse of the DCFT. So it's integral over the period, which is 1 over delta. Rather than little f of t, it's capital F of nu. And then rather than e to the minus 2 pi I nu and delta, it's plus because it's the inverse transform. So 2 pi I and delta nu, like so, d nu. Okay. All right, so that's the inverse of the DCFT. Okay, and the proofs are rather elementary. Okay, so to get injectivity, what you need to do is you need to show that if the DCFT of something is 0, then the function must be 0, and you can prove that, just by well, let me do it. It's easy. Okay, and it really just uses little L1-ness of f. Okay, suppose that f dc of f is equal to 0. Okay. All right. Thus, okay, I have that sum n in z f of n delta e to the minus 2 pi I n delta nu is equal to 0. Okay, and so this is 0 in the codomain of the DCFT, and the codomain of the DCFT is C0. Okay, so that means that this is equal to 0 for every nu. Okay, so then I integrate. Okay, so I'm going to integrate from 0 to 1 over delta d nu, this equation. Okay, so so I'm going to get the integral out here, but because this converges uniformly by virtue of little f being a little L1, I can pull the integral inside. Okay, so I'm going to integrate from 0 to 1 over delta. And I'm going to put the integral inside the sum by uniform convergence. Oh, sorry. I forgot to say I'm integrating 2 pi I m delta nu d nu. Okay, so I'm taking an arbitrary m and I'm integrating by that function, with the product with that function. Okay, so it's e to the minus 2 pi I. Well, let me combine the exponentials. 2 pi I m minus n delta nu d nu. Okay, and I've calculated this integral 1,000 times before. Well, I think I maybe only calculated it once, but we've used its value 1,000 times before, and that is that it's when n and m are different, it's 0, and when n and m agree, then it's the period, which is 1 over delta. Okay. Okay, and so the point is then that this infinite sum degenerates into a finite term. So it's and this is equals 0, and so therefore f of m delta over delta is equal to 0. Okay, and this is true for every m, and so therefore f is equal to 0. Okay, and thus the DCFT is injective. Okay, so that's the injectivity. Now, what about the inverse transform? Okay, that's more or less the same formula, the same computation. Okay, so what I'm going to do is I'm going to take f in little l1, and then I'm going to calculate the forward transform of f. Okay, and then I'm going to calculate the integral of that by this inverse function here, which just means that I multiply by that exponential and then integrate from 0 to 1 over delta. Okay, and the point is that I get exactly the same computation. Okay, so the same computation gives f c inverse of f c of f equals f. Okay. All right, so inversion of the DCFT is elementary, is the point. Okay, and it's really just because the domain of the DCFT is little l1, and little l1 gives you uniform convergence of that sum defining the DCFT, and that's the easy part. Okay. Now the L2 DCFT. Now the L2 DCFT bears stronger resemblance to the L2 CCFT than it does to the L2 DCFT, and that is because L1 of Z delta C is contained in but not equal to L2 of Z delta C. Okay, and so if f is in little l2, then we cannot directly apply sum to calculate DCFT of f. Okay, because that for that sum to kind of make sense in a unambiguous way, f the sum ends should be in little l1, which amounts to f being in little l1. Okay, so but you can very easily retrieve something that makes sense in exactly the same way as we did for the CCFT, and moreover we get something that looks quite familiar to us. Okay, so we thus define the DCFT on little l2 in a way that it's similar to CCFT. Okay, so that is to say, I take f in little l2, okay, and I define a sequence fj, okay, to be I again chop off f Okay, from minus j to j. Okay. So then, so notice, and this is an obvious statement now, it wasn't that difficult in the continuous time case, but here in the discrete time case, it's perfectly obvious. So Fj is in little L1, intersect little L2. Okay. And it's also obvious that the the DCFT of Fj is in L2 per, sorry, not T, 1 over delta. Okay, so this is obvious because Fj is a function with finite support, right? So by truncating it like this, I just get Fj will have finite support, and therefore its DCFT will be given to me by a finite sum of harmonics, which will certainly be in L2. Okay. Okay. Moreover, C of Fj is a Cauchy sequence in L2. Okay, and define FDC of F to be the limit of these things. All right. Right, entirely analogous to what we did for the L2 CCFT. So note, except for the minus sign here. So when we talked about Fourier series, we had a very similar formula, except it was time instead of frequency, and we had no minus sign there. But other than that, this is the same theory as the L2 L2 Fourier series. So except for trivial differences, the L2 DCFT is the same as L2 Fourier series. Okay. And so remember, the Fourier series were posited as the inverse of the CDFT. Okay, so this is telling us that the forward transform for the DCFT in the L2 case is the same thing as the inverse transform of the CDFT in the L2 case. And, we also saw up here that the same statement held in the L1 case. Okay, so the inverse transform for the DCFT is the same as a forward transform for the CDFT with minor and uninteresting inconsequential differences. Okay, and you'll be unsurprised to learn, of course, right, so This is a Hilbert space isomorphism. Okay. Very nice. Okay, so finally, I'll finish up today since we're here. Okay, and we'll talk about the final of the transforms and, theoretically the easiest one. The DDFT. So it's theoretically the easiest one, but it's also the most practical one in the sense that if you ever do, applied work, with hardware and actual signals out in the world, and with actual measurements, you're working with Fourier transforms, you're almost certainly going to be using the DDFT. Because when you store data, you store discretized data. And so when you transform it, really the only thing you can do is take a DDFT. So it's discrete, and it has a finite interval on which you've taken the data. And so then what you do is you kind of periodify it, and there's some thinking you have to do about that. But what you end up with naturally when you calculate Fourier transforms there is the DDFT. Okay, so let's just get to it. Okay, and so discrete time and discrete frequency. So what this means is because I have discrete time and discrete frequency, that must mean that I'm periodic in time and also periodic in frequency. Okay, so these things are periodic and discrete time in both time and frequency. Okay, all right, so we're going to start with F. And so the hardest part of the DDFT is sort of getting all the frequencies correct and the frequencies and periods. Okay, so we're going to take F in T periodic. So then T must equal N delta for some N. Okay, and I'm going to denote by little l per N delta of the T periodic signals. Okay, and so I don't need to put any kind of an index up here, L1 or L2 or little c0 or anything like that. And the reason is this, is that because these are periodic and discrete time, this space is actually finite dimensional. Okay. And so membership in here doesn't require any norm conditions. And so we don't need to fuss with that kind of stuff. So that's one of the reasons why the DDFT is kind of theoretically straightforward, is the spaces involved are finite dimensional. It's also one of the reasons why it's practically simple, because you're just talking about a linear transformation between finite dimensional vector spaces. So you can represent the DDFT by a matrix. Okay, so this then is the domain of the DCFT. What's the codomain going to be? Okay, FDD of F. Okay, so the transformed signal, what do we know about that? Well, we know that because the time signals are periodic, with period n delta, then the frequency signals will be sampled with a sampling interval of 1 over that. Okay, so we know that we're going to have discrete frequency signals with a sampling interval of 1 over n delta. Okay, so that's one thing we know. And because the time variable is discrete with a sampling interval of delta, we know that the frequency signal is going to be periodic with period 1 over delta. Okay, so it's then sampled, so discrete time, discrete frequency, with sampling interval 1 over the period of the time signal, okay, and periodic with period 1 over the sampling interval of the time signal, so 1 over delta. Okay, and so you'll notice here that, you know, n times 1 over n delta is 1 over delta, so it all fits together. All right, and so therefore the DDFT is going to be a mapping from L per n delta z delta c into L per, okay, so the period is 1 over delta, z of 1 over n delta c, okay, and we have a formula for it. Okay, and that formula is f d of f, okay, at k over n delta, okay, because it's a member of the sampled frequency domain with sampling interval 1 over n delta. Okay, so it's going to be, you're going to sum over a period. Okay, so it's going to be from n equals 0 to n minus 1, because the period is n delta. Okay, f of n delta, then it's e to the minus. Okay, and so the rule is that it's 2 pi I nu t. Okay, so t is k delta, right? Sorry, k over n delta. K over n delta. Nu is going to be oh, sorry, I apologize. Sorry, I had it right the first time. T is n delta, right? So that's T, okay? Okay, and then the frequency is k over capital N delta. Sorry. Nu is k over n delta. Okay, and so when you combine all this together, this is 2 pi I. So it's so you have various ways of organizing this. So I'm going to organize it like this: k over n, n. Okay, so it's e to the minus 2 pi I n k over n. Okay. All right, and then finally, because this is Fourier stuff, and I have a sum over discrete frequency in this case, I need to put the sampling interval up front. So 1 over n delta. Oops, sorry. Oh, right, sorry, yes, apologies. So the sum here is over time, and so the sampling interval in time is delta. Okay. The inverse transform will have a 1 over n delta. Okay, so in any case, there's your DDFT. So like I said, the hardest part is getting everything right. And so one of the things you notice here is delta doesn't show up here. Okay. And so for that reason, you will very often see the DDFT defined without fussing with the sampling intervals and the periods. Okay, so the sampling interval will be 1 and the period will be 1. And because of the formula, and so this would just be, you know, n without the delta there, and then delta doesn't participate here, and so everything sort of works out without having to fuss with all of this stuff. However, I think including all of the stuff is a very good idea, because it tells you naturally. So for example, these things normally arise, DDFTs normally arise from sampled continuous time signals. And so there is a natural sampling interval there, okay? And they're going to be measured for a certain time. So there's going to be a natural period there. And I think it's better to keep track of these things, okay? But almost all the time, people do not do what I do here. And it's just n here and k here. Okay. All right, so the DDFT is a linear mapping between finite dimensional vector spaces. It is invertible with inverse. Okay, so now this really is an inverse. Okay, so I'll write the frequency signals with a capital F. Okay, so these are going to be of k delta. Okay. All right, so this is going to be sum n equals 0 to n minus 1. It's going to be f of n over n delta e to the 2. So the exponent is kind of going to look the same, except the roles of time and frequency will be transposed. So I'll write it like that. And then you need to put the sampling interval, and now it's at sampling interval 1 over n delta, so that needs to go up front. Okay. And so to check that that's the inverse, just stick that. Oops. Stick that into there and do some computation. All right. So moreover, if we define inner products, okay, so now I have a time inner product and a frequency inner product. And the difference between these things is the sampling interval, of course, but also the factor that defines the inner product up front here, okay? So I'm going to have f, g, and I'm going to call the time one like so. All right. And so that's going to be sum n equals 0 to n minus 1, f of n delta, g of n delta, right? And then delta out front, okay? Because that's the sampling interval in this case. The frequency inner product, writing my frequency signals as capital F and capital G, are same formula, but with the appropriate sampling intervals. And then the appropriate factor up front to bookkeep the sampling intervals, right? So if we define the inner products like this, then FDD is Hilbert space isomorphism L per of right, so the period here is n delta delta C with the inner product time 2 L per that's right. 1 over delta of Z of 1 over n delta with the frequency inner product. And to me, this is a tour de force of the notation. The choices for putting scaling factors out in front of the summations in the both time and frequency, because as long as you do that, including in the definitions of the inner products, then you know the DDFT actually preserves the inner product. Okay. All right. Good. Examples. And I'll look again at the same two examples that we talked about for the other transforms, just to complete the circle there. All right. And so I'm working now with discrete time, discrete frequency, okay? And so I have, and you know, so there's some fiddling that you have to think about here. Let's assume that n is even for simplicity. Okay, and so the a period goes from minus n over 2 to n over 2. Then I'm going to go from minus m to m. And sorry, I'll put the delta in there. Okay, and then the first one, it's going to be the sampled rectangular window. Sampled and periodic rectangular window. Okay. Then the DDFT, okay, so what should it be? It should be periodic and sampled. So of course it's going to be the sampled periodic Dirichlet kernel. So, and then you get this factor of delta out front that comes from our definition of the transform. But other than that, it's just the sampled periodic Dirichlet kernel. The period is 1 over delta. Okay, and the n in the periodic Dirichlet kernel is the m. Okay, absolutely beautiful. So you take the in the continuous time aperiodic case, you take the windowed function, the rectangular window function, and then you do two things now. You sample it and you periodify it, okay? And then what you do in the frequency domain is, because you sampled and periodified in the time domain, you periodify and sample in the frequency domain. Okay. Similarly with the Fourier kernel. Okay. So here we're going to take the triangular window, like so, and then you apply the DDFT. Okay, and you get the sampled periodification of the Fourier kernel. Okay, you need to make sure that all the constants and everything work out, but the point is they do. All right. Okay, so that's our sort of basic discussion of the DDFT, or sorry, the CDFT, the CCFT, the DCFT, and the DDFT. We will talk a little bit more about some other attributes of these things the next time, and I'll say some more precise things about this interconnection between sampling and periodification. So I'll do that next time, and then after that we'll start talking about very quickly go through the story of Fourier transforms. And so this means both of the continuous time transforms, the CDFT and the CCFT, is applied to distributions. Okay, so that's where we're headed next.